Hello students, in this class we shall study about ideal gas laws, and these are the laws. First comes Boyle's law, then comes Charles' law, and then comes Avogadro law. And by combining these three laws we get ideal gas law. Now before we come on to Boyle's law, we have some assumptions of ideal gas. What are these assumptions? First is that the molecules are dimensionless. And they are only point masses. Point mass. Molecules are only point mass. And second is molecules move in random direction. So in ideal gas, the molecules are moving in random direction. This is a container, gas container, and it is fitted with one piston, movable piston, and it has got some pressure P, volume, and temperature. And let us suppose there are n mole of gas. N is the number of moles of the gas. So in this diagram, the molecules are moving in random direction and they collide with each other. The molecules collide with each other elastically. Elastically means there is no loss or gain of energy. This is elastic collisions. And fourth is there is no electrical force between, no force of attraction or repulsion between the molecules. And fifth assumption is that pressure is created by the collision of molecules with the walls of the container. So these are some of the assumptions with our ideal gas model of the gas, but in the real gas, these assumptions are not applied, and hence real gas is different from ideal gas behavior. Now these laws are only applicable in ideal gas, and a real gas at very high temperature and very low pressure, it behaves as nearly ideal gas. So now we take the laws one by one. First we take Boyle law. Boyle's law. See, there are four parameters: volume, pressure, temperature, and number of moles. In Boyle's law, this is the relation between volume and pressure. Volume is inversely proportional to pressure. This is called Boyle's law. And constant number of moles and temperature is kept constant. This is called Boyle's law. Volume of a gas is inversely proportional to pressure. How? Let us take this example. If we apply some pressure on it, this piston will move here and the volume of gas will decrease. If P is increasing, then volume will decrease. This much of volume will be there after applying the pressure. So Boyle's law says that volume of a gas is inversely proportional to the pressure of the gas. Second comes Charles' law. Charles' law, volume is directly proportional to temperature, and here pressure and number of moles, that is kept constant. And see, if temperature is increased, then keeping pressure and number of moles constant, then volume will also increase, because increasing the temperature will increase the kinetic energy of the molecules and they will expand to increase the volume. Now third is Avogadro law. This is volume is directly proportional to number of moles, keeping pressure and temperature as constant. So if we combine all these three, number 1, number 2, number 3, then we get that V is equal to, V is directly proportional to NT by P. Or in other words, we can say that PV is directly proportional to NT. And now this can be replaced by this by putting a constant. This is constant of proportionality. Constant of proportionality, and this is called gas constant. Molar gas constant, PV is equal to nRT. This is ideal gas law. PV is equal to nRT, and R is the ideal gas constant, that is its value is 8.3145 joules per Kelvin per mole. This is the value of ideal gas constant. Now let us see what does this PV is equal to nRT, PV has another significance. This is the work done by the system. When temperature or number of moles are changed and pressure or volume is changed, any of the parameter is changed, then some work is done by the system, and this work done is represented by P into V. How? Let us see. This is the system of gas. This is piston here, and here are molecules in this system. Now if we give heat to this system, what will happen? This gas will expand and volume will increase, temperature will increase, then the piston will reach here and the volume will increase to this. So the system will do some work on this piston, and piston will move by this distance, let us say it d. So pressure is, what is pressure? We have studied in our earlier classes that pressure is force per unit area. And what is volume? PV, force divided by area into volume. Volume is area into distance. So A cancels out with A, and we are left with PV is equal to F into force into distance. And force into distance, we have studied in our earlier classes that it is the work done. So the significance of PV is equal to the work done by the system when any of the parameter is changed. Now we come on to the Avogadro number. One concept of today we shall study about Avogadro number. See, at STP STP means standard temperature and standard pressure. Standard temperature is 0 degrees C, or in Kelvin it is 273 Kelvin, and standard pressure is 1 atmosphere. If at STP the number of moles is equal to number of moles of a gas is 1 mole, then number of molecules in gas will be 6.023 into 10 raised to the power 23. This is the number of molecules, and its volume at STP will be 22.4 liters. this number is called Avogadro number, and it is represented by an A. So this is the Avogadro number, and now we come to Boltzman constant, and relation between Boltzman constant and ideal gas constant. See, we have studied that PV is equal to nRT. This is the ideal gas equation. This is for N is for number of moles. If we, instead of taking number of moles, we take instead of number of moles, we take here, this is the ideal gas equation. Okay, ideal gas equation. In this equation, if we take instead of number of moles, instead of this, the total number of molecules are taken, and total number of molecules represented by capital N, this is equal to number of moles into Avogadro number, because Avogadro number is the number of molecules in 1 mole. So number of molecules in n moles will be n into Na. So what we do, PV divided by RT, or let us say that it is NT, it is equal to gas constant. If in place of this we take the total number of molecules, then PV NT for taking total number of molecules, what we do, we divide by Na. PV then this is R by Na. So it becomes this R by Na, this is called Boltzman constant, and these are the total number of molecules. Then our gas equation becomes PV divided by NT is equal to Kb. And what is the relation between Boltzman constant and gas constant? See, here we get that R is equal to Kb, Boltzman constant, into Avogadro number. And if we see it numerically, arithmetically, then Boltzman value of Boltzman constant is 1.38 into 10 raised to the power minus 23 joules per Kelvin. And if we multiply it by Avogadro number, we get 8.3145 joules per Kelvin per mole, and this is the value of R. It means Kb into Avogadro number is equal to R. This is the relation between Boltzman constant and gas constant. So thank you for watching the. Today we shall study about Boltzman constant. See, Boltzmann constant is represented by Kb and its value is 1.38 into 10 raised to the power minus 23 joules per Kelvin. Now, it tells us energy is directly proportional to temperature. It relates the relation between energy and temperature of a system. Then it is kBT, energy of the system is kBT, where kB is the constant of proportionality. See, here we can say that the molecules are moving in all the three directions. This is x-axis, this is y, this is z. So molecules are moving in this direction, 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 and degree of freedom of movement of molecules along x-axis it is 2, along y-axis it is 2, this and this, positive y and negative y, and along z-axis it is 2. So average energy along one axis it is kBT divided by 2. And if there are three axes, then we can say that total energy is equal to 3 kBT by 2. But this is for one molecule, and for n number of molecules it will be E is equal to 3n kBT divided by 2. Here kB is the Boltzmann constant and its value is equal to 1.38 into 10 raised to the power minus 23 joules per Kelvin. Now we shall do one more topic, and that is derivation of ideal gas equation on the basis of kinetic theory of gases. How can we drive it? This is very interesting topic, and we can see that the molecules in a gas, if this is the container is here it is L. Length of one edge of the container is L, and this is a cubic container, and number of molecules in this of a monoatomic gas is contained in this container with a length of an edge is L. Suppose here it is one molecule that is moving towards x-axis and its velocity is ux. So now we say that F is equal to, what is force? Force is rate of change of momentum. Rate of change of momentum. Or F is equal to delta P by delta T. What is the change in momentum? See, if it strikes with the wall, the molecule strikes with the wall, then with the velocity ux, and as the collision is elastic, then after collision the velocity of the molecule will be minus ux. Then change in momentum will be mux minus mux. That will be 2mux. And then force is equal to, see, force is equal to delta P by delta T. It is equal to 2mux divided by delta T. And see, delta T is equal to d by s, distance travelled between two collisions, and s is the speed. So distance travelled between two collisions is L, this L, and again this L. So it will be, distance travelled will be 2L. So distance travelled is 2L, and speed of the molecule is taken as ux. Then we replace delta T by this value. What we get? Let us see. F is equal to 2mux divided by 2L and into ux. This becomes, 2 cancels out with 2. This becomes mux square divided by L. So this is the force. Now pressure. What is pressure? P is equal to pressure. This is force per unit area, and area of the edge is F by L square. Okay, now we see what happens. P is equal to, force is equal to mux square divided by L, and divided by L square, divided by L square. This becomes mux square divided by L cube, and L cube, length into length into length, it becomes volume. It is volume. So we get PV is equal to mux square. Now let us see what happens next. We have taken the velocity of one molecule along one axis, only x-axis. So we have to calculate the root mean square velocity c square, which is equal to ux square plus uy square plus uz square. The square of the velocities in all the three directions when taken then that will be when some of these velocities are taken along all the axes, then we get the root mean square velocity. Then by convention we know ux is equal to uy is equal to uz. All the three velocities are equal. Then we can write it as ux square plus ux square plus ux square. All the three are equal. This is equal to 3ux square. And when it is 1 by 3 c square is equal to ux square. So we take this value of ux square and replace this value in this equation. PV is equal to mux square. PV is equal to mux square, which can be written as 1 by 3 mc square. Now, if we multiplied it both sides by 2, by 1 by 2, then what we get, it is 3 PV by 2, it is equal to 1 by 2 mc square, and this is the kinetic energy. C is the velocity, this is the formula for kinetic energy. And by Boltzman we know that E is equal to 3 by 2 nkbt, and here potential energy is 0 because there is we have assumed that there is no force of attraction or repulsion between the molecules. Hence in ideal gas potential energy is 0, and this whole internal energy is only due to kinetic energy, and that is equal to 3 by 2 nkbt, which we have studied, and this is equal to this. So we can say that 3 PV by 2 is equal to 3 by 2 nkbt. 3 by 2 cancels out. PV is equal to nkbt, and nkb here is equal to R, which we have studied, and it becomes R is equal to nkb. Here R is equal to kb and A, and if we divide this equation, see, if we divide this equation by Na, KBNA Avogadro number, then it will become equal to NR, and then it becomes PV is equal to nRT. Okay, then we get the equation PV is equal to nRT, and this is the ideal gas equation. Here PV is equal to, this is total number of molecules, and total number of molecules is equal to number of moles into Avogadro number. Now we replace it with PV is equal to NA KBT, and here KBNA is equal to R. Hence we get the equation PV is equal to nRT, and this is ideal gas equation. So we have derived this ideal gas equation on the basis of kinetic theory. Thank you for watching the video.